Hello, it's Keith here, and this is lesson 19 of the multi-platform series of my Z80 assembly programming tutorials. Today we are looking at the speech synthesizer that we looked at last time. This is part 3 of the 4 parts. Now, the speech synthesizer, in case you've not seen the previous episodes, was something I reverse engineered. I disassembled it, so it was a compiled binary. I disassembled it, I code commented it, I made some improvements to it. And so we discussed the improvements and the optimization and the disassembly in the past 2 lessons. This time we're actually going to look at the first half of the source code. The part we're going to look at today converts the string that you pass to it into a phonetic equivalent that can be then used to select the sound samples to actually play back the audio that is the text that you wanted to play. So that's what we're going to look at today. Let's go over to the source code and let's take a look. Now, as always, you can get the source code from my website. You can run this yourself. It's called speech_final. However, as I've said with the past 2 lessons of this, unlike all of the rest of my tutorials, which I've written myself and you can use in any way you want, this is someone else's work and it's technically copyrighted, but back from the 80s. So if you are concerned that that person might come back and sue you, or that company might be still in existence and sue you, you have to make your own choices. But as I say, I'm providing this for educational purposes. If you want to do anything else with it, you're fine from my point of view, but you have to bear in mind that it is technically copyrighted reverse disassembled work. So on your own head be it. That's all I can say there. Now let's just fire up the example and let's actually hear it say its thing. We will use the master system because that is the fastest to start up. No pesky operating system. Sorry, the screen's going blank there. That's the that software is running the legacy mode at the moment, and that messes up OBS there. Anyway, so that's the speech, and the speech, as you heard there, is my comedic comment. It says, "I am a master system, you are a worm. You will bow to my Z80 superiority." And you can see I've put different versions because I've modified this code. The original version only worked on the Amstrad CPC. The modified version can work on any Z80 system. I've coded it up for these, but that's just because these are the ones that support 4-bit sound. Anything lower would get a bit pointless. Anyway, so that's the speech we're going to play. And to actually sort of play that back, what needs to happen is it needs to be converted. Now, the conversion happens in 2 stages. The first stage is a kind of a processing stage. These have been copied straight out of memory, so this is exactly what it would have used. I am a CPC, you are a worm, you will bow to my Z80 superiority. Now, basically, it's shifted it into uppercase for matching. It also adds a space to the start, though that's got lost there. So it's just that's the initial stage, and then what it does is it converts it into these things here. Now, this is the actual letters that are going to be used to select one of the sound samples for playback there. So that's what that is, and you can see you've got these numbers. I think those were a delay. I think the numbers were a delay. Unlike most of my tutorials here, I'm going to have to be a little bit more hazy in some places about what exactly the code is doing. There's like one point in today's lesson that I'm a bit unclear on, and that's because I didn't write it. I managed to reverse engineer it enough to make some optimizations. I managed to comment all the code, but without going through like step by step on every single thing and looking at every single byte flow through the system, there's just one little bit that I'm a little bit fuzzy on, so I apologize for that. But as I say, that is kind of the risk of disassembly, and as I've said before, if you can't write something yourself, you're probably going to struggle to disassemble it for that reason, that you might not understand what you're looking at because it might never have occurred to you to write that because it's not your code. Anyway, so when we actually want to say a string, we're going to use this say string from HL. We load the address of the string we want to play, and the string we want to play is 0 terminated, so all pretty straightforward there. Now, the playback routines need some memory, so we've got various variables we're defining here. We'll see them in the code. I'm not going to go over them here. There's a quick description of them over here anyway. The variables you can see, there's very few of them. There's only about 32 bytes or so here, but at the end of this there is something called text raw string. This address is used to convert your input into the intermediary, which goes immediately at that address, and then immediately after that again this data is stored, which you can see is slightly longer. So you need about 3 times the memory at the end of this block of variables there for those 2 converted strings for this code to work. So that's just what you need. So the good thing is, though, the original version, it stored it at 2 fixed memory addresses in completely different places, and I modified it to combine them together to at least be a bit more memory efficient. Anyway, so that's the start of what we're going to look at today, this loading in routine. And so let's take a look at that and let's see what actually happens from the point of view of processing. So here it is. So when this is executed, HL will contain the memory address of the string we want to play, and the accumulator contains the speed, which it should be in a range of 0 to 15. Now this is used as basically as a sort of a loop to make the pitch of the sound change, so you can make the pitch higher and lower by altering this, but it needs to be within a specific range, otherwise it won't work properly. And so you can see here this is being complemented, flipping the bits and then adding 1A, and it's expected to be in a range of 0 to 15 for this to work. That's then being stored into this speech speed here, which is used later on in the playback code. Now what we're doing here then is we're moving the address of the string we want to play into DE here, because we're going to use HL and we're going to prep up the temporary data. We need to start with a space. That's because the code uses spaces as between words, so the first word needs a space before it. That's what it's doing there. And then this code I actually converted. The original, there were multiple processes here. There was one that looked for the last character, and there was one that added the character 13 to the end, and I'm not sure if there was a third one as well. It was a bit looser than it could be. So I've combined some of these together into a single routine. So this is adding the space at the start, copying all of the characters until it gets to a 0. You can see all A is comparing to 0 there. And then once it's done, we will end up down here. Now what it's then doing is it's storing the last character in the string. Now this is something that's quite interesting. The code has a routine to check if the end of the sentence is a question mark, in which case it shifts the pitch up of the vowels, I think it is, at the end of the speech. If it's full stop, it shifts them down. As I say, I think it is, because again I'm having to reverse engineer the code and work out what it's actually doing, but I'm pretty sure that's what it's doing. So that's why we're storing the last character there. That's what that's for. And then we're now character 13 terminated, not character 0. We're then running a subroutine called charfix. I mean, I guess maybe I could have merged this one together, but it felt a bit heavy. So charfix is the first processing routine. And so what this is doing here, you can see here, is basically we're seeing if our letter is between A and Z in lowercase. If it is, we're converting that lowercase to uppercase by subtracting 32 there, hexadecimal 20 there. So that's what we're doing there. So converting everything into the uppercase, you can see here, and that's so we can match to the conversion tables. So that's what's happening here. We're also comparing to this character here. That's because that has a special meaning in the translation table, so that's why we've got that. Now, once we've done that, we are basically just repeating here. Now, you can see here if we've got this character here, we're swapping to spaces, but basically that's all we're doing. So that's just fixing up the characters and converting them initially to uppercase. Now, once we've done that, we've now completed this initial string here. So you can see what I'm doing here is I'm inking HL, and then I'm keeping this for later because, as I say, I store this second string immediately afterwards, which isn't something the original code did. What we're then running is we're running convert to phonetics. Now, this will create this rather weird version. I don't know anything about speech synthesis except for like scraps of information I've heard, anecdotally, but I don't know that this is like an official syntax. I did try and look it up and I couldn't find anything that looked like that, but I really don't know. I say I am far less than an expert on this. I just have very, very vague knowledge on it. Anyway, the convert to phonetics routine, what does this do? Well, this is going to actually sort of convert the string. The source string is now at text raw string, and we're going to process that, and we're storing that temporary position here. We are resetting HL switch address 1 and 2. Now these are used to remember the positions of those vowels that we might need to change the pitch up or down if there's a full stop or a question mark. So we're just starting those off at 0 here, and then we're running the cool translate to phonetics routine. That will convert, and then we are storing a character 13 at the end, and then we're returning. So that's what we're doing here. So here is the translate to phonetics routine. So we're loading in the address of the string we want to convert here. We're loading in the next character, and we're comparing that to the end of the character return, which is the end of the string. We put that in earlier, and if it is, we return. Otherwise, we're going to find a lookup, an entry in the phonetic table, and then we're going to transfer it, and then we're going to repeat. So that's what we're going to do there. Okay, so here is the lookup routine. So what this is going to do is it's basically going to try and find a match within the lookup table for every possible source piece of text, which might be a whole word or part of a word, and then the phonetic replacement. So if we look at the further down in our code, those are the wave file, those are the wave sound samples. Here is the phonetics table. So you can see here very clear the word David with a space before and an after is converted to DAYVIDHD, and PSY is converted to SIY, and so on. So psychic would be SIY KIC or something. So you can see here we've got various parts. Now this is split into sections. I've split this out for clarity. You couldn't see these separations in the original binary, but basically you can see there's a section here for spaces, there's a section here for letters starting O, there's I, G, there's every letter in the alphabet here, there's one for numbers as well, here it is down at the bottom here, and question mark, it has a special purpose. You can see there's a question mark here in this one and in this conversion here. And this basically replaces this character. It takes this character that is in the question mark here and puts it in this position here. And you can see there's this sort of catch-all one here right at the end here. And that will basically catch anything that's not been caught by something else. So that's how that works. And you can see we've got this list of pointers to the A to Z sections here. Now pointers, of course, these are 16-bit values, so that's 2 bytes, and we're going to use those in just a moment. Okay, so let's take a look at what our phonetic matching routine does. So this is what we'll be executing here, and we've loaded in a character, and we're now basically seeing if it's a letter. And if it is a letter, we're going to end up here. If it's a non-letter, we're going to branch out to a separate routine that we'll look at in a moment. Now, if it's a letter, what we're going to do is we're basically subtracting the letter A. And so if we go from A to Z, we're now going to go from 0 to 25. Now, what we then do is we basically double that value. So it's now 0 to 50. And that's because there's 2 bytes per entry in our lookup table, you see. And we're adding the address of that lookup table to what is now the offset of the one we want to use, and we're then loading in the address from that offset and storing it into conversion address here. And the reason for that is quite simply what we're basically doing is we are selecting one of the addresses in this lookup table here and then jumping to the phonetic conversion table for the letter, matching the letter that we've just found to try and find a valid conversion for that letter. Okay, so we've got our address of the lookups we want to use. Now what we're going to use is we're going to use phonetic match test to try and find a conversion. Now if we find a match, we will then get the carry set, and so we will return. If we don't get a match though, we're going to have to skip over the phonetic. This is basically going through pairs of entries because each pair is a source and an equivalent phonetic. So we're going through pairs of entries each time, and so we're just testing one here, and if it doesn't match, we're then going to test for the next one, and we're going to keep on until we find something that'll work, because that question mark will catch everything. So that's what we're doing here there. And so what we're doing here is we're skipping over a pair that didn't match. This is quite clever. I wouldn't have thought of this. So what we're doing is we're using CPIR, compare, increment and repeat. We want to find 2 zeros because each of the phonetic matches, the source and the equivalent conversion, have a 0 byte in between. So we want to go past 2 0 bytes to move to the next one, the next pair. So that's what we're doing here. We're loading the accumulator with 0 because we want to find a 0. I've set this to 255. That's more than enough to, there's no conversion pair that are 128 bytes, so that's more than enough. And so we just do 2 CPIRs, and that basically moves the HL position past those 2 conversions, and then we repeat and try the next one. So basically, eventually we'll find something that we can use as a conversion, and it's this that's doing that work. Now, the only exception to this, of course, was those non-letters ones you saw before. If it wasn't a letter we were converting, we use lookup non-letter, and that decides to either use the spaces, or if it's not a space, we use the number table. So hopefully one of those will match. Spaces is for whole words because sometimes there's a good whole word match, but that's what those are doing. Now the testing routine you can see is here. So basically what this is doing is it's loading in our source and our converter, and we are basically taking each character from the source. We're seeing if it's a space, and if it is, we're jumping down to here and we're carrying on. If we haven't got a space though, we are checking for question mark. A question mark, as I say, is a special one where we do an equivalence replace. The question mark in the equivalent is copied from the source. So in that case, what we're doing here is we're checking we've not got a character 13 at end of line in the source, and if we haven't, we're storing that conversion in this temporary variable character form string, which will be used if this phonetic turns out to be acceptable. Okay. What we're then doing is we're comparing to our source character and seeing if it actually matches. Now, if it doesn't match, then this is no good. This isn't a possible solution. So we're basically clearing the carry here. That XOR there is actually to clear the carry, and then we're returning this one's no good, so we'll have to try something else. Now, at this point though, this character seems to be okay, so we're going to repeat. So what we're doing here is we're moving to the next character in the source and the destination. We're checking if we have reached the end of the conversion, the source for the conversion in the phonetic table here with the 0, or the end of our string with the 13 here. And then we're loading in the next character and we're repeating. although actually, looking at it, I think I could have made a 1 byte saving there. If I'd moved that up there, I think I could have saved an extra byte. Anyway, not a major problem, but just noticing some duplication there. Now, if we've got a 0 here, then we've reached the end of the source conversion in the phonetic table, and so this must be a valid solution for this code, for this part of the phrase we want to convert. So what we're doing here is we're updating BC and HL. Now, BC is the source, so we're moving the source to the phonetic equivalent, and then we're decrementing HL here by 1 here, and we're storing that string pos there. Now, this is the bit that I'm a little bit hazy about what exactly is going on here. As I say, I didn't write this, I just assembled it. So it's stepping back through BC by 3 bytes and seeing if that's a 0. So seeing basically if the source phonetic is only 3 letters. And it's basically adjusting the HL source string accordingly. And so I guess this is walking back by the equivalent amount, but it just seems a little bit weird there. I don't quite understand why that's doing that, but anyway, that's what it's doing, and it works. So I'm happy if it's happy, kind of thing. And then it's setting the carry to mark that this was a successful conversion and returning. Now that carry, of course, was being used up here when we were looking for a valid conversion. So when we found that, we then return. So this is the calling routine, and this was being called up here. So once we found a valid match, we then run transfer entry. So the phonetic transfer entry is going to use the converted phonetic and build it into the string equivalent of what we want to say. So we've got our valid conversion now in BC here. We've got the address of the translation we're building in HL. That's this thing here. So we've got that, and we're going to transfer letters. So we're loading in a letter from BC. If it's a 0, we're already done. Otherwise, we carry on. If it's not, if it's a question mark, then we're going to use that character that we loaded in from the source string. Remember I said before, if there's a question mark in the source, then it's actually going to copy the original one here. We copied that into character from string here, so that is now going to be used in the destination there. So that's what's happening here. In other cases, though, including that case actually, we're running this thing called vowel switcher, and this is checking for the vowels, and if we find a vowel, we then run HL switcher, and this is storing the last 2 positions of vowels within the phrase. Now, why is it doing that? Now, as I said before, if the sentence ends in a question mark or full stop, it shifts the pitch either up or down, and this is selecting the vowels that's going to apply to and remembering their memory addresses for later in the actual sample playback routines. So there's 2 of them here, and that's what it's doing here. So the first one is stored in HL1, and then the second one is stored in HL2, and the toggle is being used to remember which one is being done at the moment. So that's how that works. So that's what that's doing there. Now, once we've done that, though, we're simply storing the converted phonetic back into the HL string, and we're repeating until we're done. And all of that will effectively create that from that using all of that. So, as I say, very complex stuff, and I can't claim to really understand the logic behind the process, which isn't to say that they've not done it right. I'm not saying that at all. I'm sure they have. All I mean is I understand conversion of strings. I understand reading memory addresses. I understand playing samples on a CPC. I don't understand the processes that are commonplace for converting text into machine pronounceable speech. I know nothing about it, and that's why I reverse engineered, disassembled this rather than write it myself, because I'd have had to study thousands of books to learn the expertise of writing your own Siri or something, which I didn't really fancy doing. I just wanted to play around with some speech synthesis on systems other than the CPC. Anyway, if you liked what you've seen here, please like and subscribe. Stick around. Next time we're going to look at the other part, which is the wave playback, which I basically totally rewrote, to be honest. So that's that's very different from what was originally there. Interestingly, this code I was quite impressed with, because it was very tight, reasonably speaking, pretty tight and very nicely optimized, shall we say. It seemed to be, at least. But the wave code, they just didn't seem to try at all. Here, I found a few tweaks and optimizations. The wave part, it just seemed like maybe they were running out of time writing it. It could literally be true. So I made a lot of changes to that, but not so many to this. I've ported this to other systems on Z80. I've also ported it to 6502, and I'm planning to port it to 68000 as well. So if you want to see that kind of thing, please stick around for that as well. Anyway, hope you enjoyed what you've seen today. Thanks for watching, and goodbye.